Imagine a future so distant, so profoundly quiet, that it defies our wildest imagination. We're talking about the ultimate end of everything we know, the slow, silent demise of the universe itself. Today, we're not just looking into the future of humanity, but into the chilling, inevitable fate of the cosmos. Prepare to witness a cosmic funeral unlike anything you've ever conceived. The most widely accepted theory for the universe's ultimate fate is heat death. This isn't an explosion or a dramatic collapse, but a gradual, inexorable fading away. It's dictated by the second law of thermodynamics, which states that the entropy, or disorder, of a closed system like our universe must always increase. Eventually, all energy will be evenly distributed, meaning there will be no more available energy to do work. Imagine a perfectly mixed cup of coffee. No hot spots, no cold spots, just uniform lukewarmness, a state of maximum entropy. For billions of years, gravity was the dominant force shaping the universe, pulling matter together to form stars and galaxies. But about 5 billion years ago, something shifted. The expansion of the universe, which began with the Big Bang, started to accelerate. This acceleration is attributed to a mysterious force called dark energy, which now makes up about 68% of the universe's total energy density. Dark energy is essentially pushing galaxies further and further apart, overcoming gravity's pull. Our universe currently basks in the glow of countless stars, but this won't last forever. Stars like our Sun burn through their hydrogen fuel via nuclear fusion. Our Sun is about halfway through its 10 billion year lifespan, with roughly 5 billion years left before it swells into a red giant and then shrinks to a white dwarf. Smaller, cooler stars called red dwarfs, which are much more common, burn their fuel incredibly slowly. They can last for trillions of years, with the smallest ones living for up to 10 trillion years or more. But even these cosmic embers will eventually exhaust their fuel and fade away. Once all the stars have burned out, the universe will enter a degenerate era. The only objects left will be stellar remnants, white dwarfs, neutron stars, and black holes. White dwarfs, the remnants of sun-like stars, will cool down over unimaginably long timescales, eventually becoming black dwarfs, cold, dark, and theoretical objects, as the universe isn't old enough for any to have formed yet. Neutron stars, the incredibly dense cores of once massive stars, will continue to exist, but they'll be silent and dark. The universe will become an increasingly desolate place, lit only by the occasional faint glow of cooling stellar corpses. Eventually, the largest and most dominant structures remaining will be black holes. These gravitational behemoths will slowly grow by consuming any remaining matter that happens to fall into them, including each other. Galaxies will merge, and their central supermassive black holes will combine to form even larger ones. However, even black holes are not eternal. According to Stephen Hawking's theory of Hawking radiation, black holes slowly evaporate over unfathomably long periods. This process is incredibly slow for stellar mass black holes, taking up to 1067 years for a solar mass black hole to completely evaporate. Supermassive black holes, like the one at the center of our galaxy, Sagittarius Asterisk, could take up to 10,100 years to fully disappear. After black holes have evaporated, what's left? Only a vast, empty expanse of incredibly diffuse particles. Even protons, the building blocks of atomic nuclei, are theorized to eventually decay, though with an incredibly long half-life, estimated to be at least 1034 years, possibly much longer. If protons do decay, then eventually, all matter as we know it will cease to exist, leaving only a sea of photons, neutrinos, electrons, and positrons, spread out thinly across an ever-expanding universe. As the universe expands due to dark energy, it will also get progressively colder. The cosmic microwave background radiation CMB, the leftover heat from the Big Bang, currently sits at a frigid 2.7 to 5 Kelvin, about 270 Celsius or 455 Fahrenheit. As the universe expands, this radiation will stretch and cool further, approaching absolute zero. The empty space between particles will become vast beyond comprehension, and the temperature will plummet to near absolute zero. While heat death is the most probable scenario, other intriguing, though less likely, theories exist. The Big Rip suggests that if dark energy continues to strengthen and its density increases, it could eventually overcome all fundamental forces. First, galaxies would be torn apart, then stars and planets, and eventually, even atoms themselves would be ripped into their constituent particles. This scenario, if the conditions were right, could happen in as little as 22 billion years in some models, but current data suggests dark energy is constant, making the Big Rip unlikely. Another fascinating, albeit unsettling, possibility is false vacuum decay. Our universe might currently be in a false vacuum state, meaning it's not in its lowest possible energy state. If a true vacuum bubble were to spontaneously form somewhere, it would expand at the speed of light, converting everything it touches into a different, more stable reality. This would be an instantaneous, universal catastrophe, completely altering the laws of physics as we know them, regardless of the exact mechanism. The end of the universe, particularly through heat death, paints a picture of ultimate cosmic desolation. Star formation will cease. Galaxies will become isolated islands, expanding away from each other so rapidly that they will eventually disappear from each other's observable universe. The very concept of forever takes on a new, chilling meaning. Time will continue, but nothing will ever happen. No new stars, no new life, no new thoughts, just an endless, silent, dark expanse. The thought of the universe ending in such a slow, silent, and desolate manner, certainly humbling. It reminds us of the precious, fleeting nature of the cosmic era we currently inhabit, an era teeming with stars, galaxies, and life. While these cosmic timescales are almost incomprehensible to us, understanding them deepens our appreciation for the vibrant, energetic universe we currently call home. It's a reminder to cherish the light before the long, eternal night. Thanks for watching, and remember to look up and marvel at the universe while it's still alive.